So when we talk about molecular polarity, we're looking at the overall, I guess, distribution of charges between the whole molecule. So, and I made an example, I think I shown you guys, you can remind me if I didn't, of CH. Okay, so bond polarity, if we're talking bond polarity specifically, bond polarity only consists of the bond between these two, between the C and the H. Okay, now molecular polarity is looking at the whole molecule, okay, the whole thing. So, okay. Now if we looked at the bond polarity between C and H, we know that it's a, is it a polar or is it non-polar?
It's non-polar.
Okay, it's non-polar. So now molecular polarity is looking at all of the bonds that are there all together and how they play a part on that molecule as a whole. So in this case, we have non-polar, non-polar, non-polar. So they are all going to cancel each other out. So the molecule is going to be polar or non-polar. The molecule going to be polar or non-polar?
I think it's going to be non-polar, right?
That's right. Because again, all of the bonds on it are non-polar, so they're not going to have an effect on it at all. So it is going to have no polarity. You're not going to have a distribution of charges, okay?
And it would be the same way if it was a polar molecule. It would follow the same reasoning.
No. Well, yeah, it would follow the same reasoning, but it would be a polar molecule, but it's different because, yeah. So would this be symmetrical or asymmetrical? Symmetrical basically meaning that you have an even distribution of charges across the entire thing, essentially. That's what it means. Asymmetrical means that you have a positive and a negative pole.
It would be symmetrical.
Okay. Simple-ish. Okay, so let's see, what about something like this? Where's mine, Betsy? She's not sharing. I expected to have a nice little package of food next to me. Okay, let's see who's here. Alan. How's your weekend, Alan?
It's all right.
Nothing's burning anymore down there?
No.
Good, good.
You're good now.
Okay. So Alan, help me out here. Let's talk about the bond polarity between carbon and chlorine.
Okay.
So what do you think the bond polarity is going to be?
It
Give me
would
your
be-
reasoning.
So the difference in the electronegativity would be 0.621, which
Okay.
makes it polar.
You said 0.621, right? Which would be
61,
polar. Yeah.
Yeah.
Okay, so we know that this guy would be polar. Okay, so now we have a polar bond going this way. Let me draw. So we have being favored in that direction there. Then we have one that's being favored in this direction here, and one that's being favored in this direction here, and one that's being favored in this direction here. So all the directions, it's being favored evenly. What kind of effect is that going to have? Polar or non-polar? So
Polar.
are you going to have, so if you're getting pulled, let's say Alan, the girls love Alan. Alan is a total, or guys, you know, whoever Alan chooses being infatuated with, maybe both, right? Now, if they're pulling you from all directions, Alan, because you're just so hot, right? You have one at each foot, one at each arm, and they're just pulling you, right? And they're all the same strength. Are any of them going to be able to grab you and say, Alan is mine?
Nope.
Nope. So in that case, is that going to be polar or non-polar?
Non-polar.
Non-polar. Is that going to be symmetrical or is it going to be asymmetrical?
Symmetrical.
Thank you, Alan. Good job. Okay, piece of cake, not too hard. I guess not.
It's only the piece
Alexandria.
of cake until the test comes.
Uh-huh. And then it's all like, what do you say? What does symmetrical mean? Andrea. I'm sorry, Andrea. Is she? Andrea, you here with me? Yeah, no, maybe. No messages. Are you there, Andrea? I know Norma is. Norma is my road dog. Norma is a guarantee. Norma, you're here with me, right?
Yeah.
See, I know my Norma. Good job. Okay, Norma, you're gonna help me out with this next one, right? So let's say we have this guy here. CHCl3. The yellows represents the the Cl3, well, each Cl, and then the white represents hydrogen, right?
Yeah.
Okay, so now the bond between hydrogen and chlorine, is that going to be polar or non-polar?
It's going to be, wait, give me a second. I have to write it down because I have to look at it.
It's okay.
They're going to be polar.
Polar, are you sure? Between carbon and hydrogen. This H and that Cl. Yeah, but the
Carbon
Cl,
and
I mean the
Oh,
Cl
no.
and the carbon and the Cl, you're right, that's going to be polar. But this one will be polar,
Yeah.
but this one will be non-polar, right? So here we have a non-polar
right.
and a polar bond, right? Two different types of bonds that are going on in the same molecule. Now, if we look at the molecule as a whole, right? So that means that we have, yeah, three guys that are just like, delicious, right? Well, yeah, we'll do it like this. Well, three guys or three girls that just say, delicious, okay? So in this case, you want to spend time with those three, right? And then you have the deadbeat guy or the deadbeat girl or whatever, who's always broke, who always like, if you guys go out, you got to pay for everything. And is always on their phone when you're out dating with them, right? And not paying any attention to you. Now, which one are you gonna want to spend more time with? The three guys that are
three.
that have everything going on for them, they're hot, they have money, and they give you attention.
Yeah, them.
You want to spend time with them, right? Okay, so then in that case, you're going to be putting all your energy towards that. So in that case, you're going to have a dipole moment, right? This jerk gets no time, right? But these three, you're going to be splitting your time up between them evenly since they're exactly the same type of guy, right? Or girl.
Yeah.
Okay, so in this case, is this polar or non-polar?
It's going to be polar, I believe.
It is going to be polar. That's correct.
I had to
Is
look
it going to be
really quick.
symmetrical or asymmetrical?
Asymmetrical.
That is correct. Piece of cake?
Somewhat.
Somewhat. It's real simple. Just think about it, deadbeats, non-deadbeats, Okay, what about this situation where you have two guys, the two that have everything going for them, right? So you're going to be giving them all of the attention. And then you have the two that you're not going to really give anything to. Jennifer, are you there? Are you with me? No, Jennifer? Kevin? In your case, women.
Sorry,
or-
I was trying to, it's
Oh,
me,
okay.
sorry.
Okay,
I was trying to work my phone since I'm not on my laptop today.
okay.
All right, so I can finally see your screen now. It used to be black. We were talking about asymmetrical and symmetrical
And polar, yep.
and polar. Okay, so what was the question?
So the question is it going to be a polar molecule? Or is it going to be a non-polar molecule?
The CHCl3?
The CH2Cl2.
CH2Cl2? Okay, I gotcha. Let me look up. Would it be polar?
It is going to be polar.
Yeah. The reason why I think that is because they're both they're both pulling towards one side, and there's
That's
no
right.
other pull going against it to kind of keep it in that one area.
That's right. So your net dipole moment will be going between the two fluorines.
Yeah.
And then, so is it symmetrical or asymmetrical?
Asymmetrical?
That's right.
Yep, because it's not the same on both sides.
That's right.
Yeah.
Okay, what about this guy right here? Let's see, who's my Kevin, since you chimed in before you got a chance to answer.
Can you hear me?
I can hear you now.
Okay. That one, I think it would be polar as well.
That's right, polar. Asymmetrical or symmetrical?
Asymmetrical.
Asymmetrical. Okay, and we've already gone over that one, right? So it's pretty straightforward, right? You just want to see if there's a distribution of charges, and if there's a distribution, then you know that it's going to be asymmetrical. If it's all even, then you know it's going to be symmetrical, right?
I want to ask a question. So in those little boxes where there's words like net dipole
Yep.
and stuff like that, what does the negative and positive signs mean?
So remember, these guys are partially negative and partially positive. So since these guys on the outside here, the chlorines, they're going to pull the electrons more towards them. So that means they're going to have not a total negative charge, but only partially negative, right? Since the electrons are being shared, but they're being shared in the extent that they're on the chlorine side more than they're on the hydrogen side, right?
Because they're more electronegative than the center atom?
That's right. Because they're more
Okay.
electronegative. And so electronegativity is the desire to pull electrons, right? If you're
Okay.
talking about that electron, we're always going to be talking about electrons when we're talking about bonding. So either remember, you're sharing, giving, or taking, right? Those are your three options. But sharing, you can do two ways of sharing. You can share evenly or unevenly, right? So if it's polar, that means you're sharing unevenly. That means that the chlorine here is getting the electrons the majority of the time, right? And then in this case, the hydrogen is getting the electrons the least amount of time. They're getting a little bit, but very little. So if you take the net charge, right? A overall net charge, it's not a full charge that they're getting, but it's a partial charge. And that's the reason why we call that partial negative, right? Rather than, you know, how like with Na isn't a partial charge, it is a full charge. So that's why we use this delta sign to mean like partial. It's not a complete charge. It's just a partial one.
Yeah, that makes a lot more sense now that you said that.
Yeah. Okay. Are we good? Any other questions? I love when you have questions like that.
Yeah, when they're polar, they'll never be symmetrical. That's only for nonpolars.
That's right. Unless, right, this one here, remember each bond was polar, but the molecule was a nonpolar molecule, right?
Yeah.
And so in that case, that one's like, it's no net dipole because everything is being pulled evenly. So that's symmetrical too, right?
Yeah. Okay.
Yeah, but yeah, usually if the molecule is polar, right, 99.9% of the time, I can't think of any time that there isn't, but I like to put that little disclaimer there. You know, usually when the molecule is polar, that means that there is a distribution of charge. So that means that it's going to be asymmetrical in that case. Okay. Any other questions before we move on? Good. Okay, so what about these cases? Here we have carbon dioxide. So the bond polarity, Steve.
Would it be for the CO2, right?
Yep. So the bond polarity between the carbon and the oxygen.
Would it be polar?
That's right, it's going to be polar. Going towards whom? This is carbon, this is oxygen. Who are we going towards? Who's more electronegative?
The carbon.
No. Remember, carbon is kind of like, I don't care, you know, if you want to give it to me, you know, sure. But if you don't, that's okay too. You can take mine, you know. So carbon is always going to be, not always, but majority of the time is going to be electropositive. So it's going to be going towards the oxygen, right? Because oxygen is going to want to get that electron. Like, hey, yeah, bring it over to me. I need it, you know. So if I have one going in this direction and I have one going in this direction, Steve, so tell me about the molecular polarity.
It's going to be symmetrical.
It's going to be symmetrical, and it's also going to be nonpolar. So that's right. Good job. So symmetry-wise, it's symmetrical. And then we know that it's going to be nonpolar for the molecule. So the molecule as a whole is going to be nonpolar, but each of the bonds were polar, right? And you can see that. So if I ask you a molecular polarity, it's nonpolar. Okay. Now, what about oxygen here in the case of water? Let's see. Okay, Kristen.
Hi. Am I just supposed to look at
Let's talk about the
The-
bonds first. Bond polarity.
oh, okay. Would it be polar?
That's right.
Okay.
And it's going to be favoring going towards whom?
The oxygen.
Just like the arrow is showing right there. Okay. So now, since you have two arrows that are going towards oxygen from the hydrogens, is the molecule going to be polar or nonpolar? Is it going to be symmetrical or asymmetrical?
It's going to be polar and asymmetrical.
That is correct. Oops. Okay, piece of cake.
Can you explain why it's polar asymmetrical again?
Yeah, so since both of these guys are going towards oxygen, oxygen is the red guy in the middle here. So again, partially positive, partially negative. Both of these guys are going towards that direction, right? So that means that overall, if we added both of those angles up together, it would be added up so that the net dipole is going towards oxygen, right? So we're saying overall the molecule is going in that direction, right? So its molecular polarity is going to be polar because the electrons are going to be around the oxygen more than they're going to be around the hydrogens. So they're only here a little bit. They spend most of their time here. So since electrons are negative, it's going to be partially negative. That's why we get that partial negative part, right? Now, again, these are covalent bonds, right? They're being shared. That means that these electrons are being shared, although they're being shared unevenly. Oxygen gets it a large percentage of the time. Hydrogen only gets it a little percent of the time, right? So since the charges are not distributed evenly, right? You don't see oxygen and hydrogen getting it the shared amount of time. That means that the charge distribution is going to be asymmetrical. It's going to be favoring oxygen over hydrogen. Do you get that?
Yeah, that makes sense now.
Okay. Okay, so that brings us to organic chemistry. Okay, so what does organic, the word organic, mean to you? Let's see, who haven't I called on? Somebody who hasn't spoken. Speak or forever hold your peace. Betsy, are you there?
Yes.
Okay, what does organic mean?
I don't know. No chemicals?
No chemicals. Okay. What about Jason? What does it mean to you?
Like things that are natural.
Things that are natural. Hector, what does it mean to you?
Living organisms.
Living organisms.
Yes.
Let's see. Cheyenne, what does it mean to you?
I would have said like no chemicals as well.
No chemicals as well? Okay, so you got all those definitions. So for chemistry, you're throwing them all out the window. They're garbage. Okay, toss them out right now. Dump them out of your head. Erase, delete. Okay, are you guys ready for the definition of organic for chemistry? You ready? It's really complicated. Now you're writing this down. Your pens are ready? Are they hot? Okay. It contains carbon. Okay, so we're looking at compounds. It's basically the study, research, application of chemicals that contain carbon. You want me to say it again? It's organic if it contains carbon. Okay, so most pesticides that we use, guess what? Contains what?
Carbon.
Carbon. So is it organic?
Yes.
My plastic bag here. This is a hydrocarbon. Does it contain carbon?
Yes.
My cell phone. The rubber on the outside, the pseudo glass in the middle, the wires, the coating of the wires, all contain carbon. Is that organic?
Yes.
Okay. So the definition of organic means it contains carbon. Now, so if you talk to an organic chemist is going to say anything that contains carbon is considered to be organic. Now, an inorganic chemist is going to say he says if it contains carbon, it's most likely organic. However, if it's a carbonate, if it's a cyanide, if it's basically a carbon, a compound that only has one carbon in it, that's a carbonate, right? The carbonate ion, right? It has one carbon in it. Well, we kind of consider that inorganic, right? But an organic chemist is going to say, no, that's organic because it contains carbon. Okay, so you'll get disputes between the two every once in a while. It may break out into a fight every once in a while. It's kind of fun to watch, because they recognize how important carbon is, right? And so you could have what some people say inorganic carbons, right? And then organic, right? So those are the two distinctions. So organic basically means that it contains carbon, and we're looking at the study. Organic chemistry is the study of carbon compounds, okay? Now, we know that carbon is such a whore, right? We know that the fact that carbon is such a whore makes it the center of life, right? The fact that it's going to form bonds, at least 4 bonds, right? It's capable of forming 4 bonds. So it'll have 4 attachments with 4 different things, right? If it needs to, So it's so willy-nilly, it's like, I could share my electrons, or you can have them, or, it's kind of like left there in the middle. It gives us a lot of flexibility. Now, because of that, as scientists, we like those complicated things that are also flexible, because that means that we could do a lot with them, right? How many of you guys like strawberries?
I do.
How many of you guys don't really like strawberries, but you love the way that strawberries smell? Anybody love the way strawberry smells?
I do.
You're the only one. Nobody else does. Everybody's like, eh. I thought strawberries was very popular over there in Salinas. You guys are close to, isn't it, what is it? No, I guess you're not close to Oxnard, because Oxnard has a strawberry festival. So.
No, I guess it's more so lettuce that we're known for, like greens.
Okay.
Not really like exciting stuff.
Okay. So how many of you guys like Kool-Aid and the way Kool-Aid smells?
I do.
You do? I love Kool-Aid. I love the way it smells, right? How many of you guys like the way that mint smells? Peppermint.
Mint?
Spearmint.
Yeah.
Yeah.
Oh,
Mint.
Yeah.
Okay. So all of those smells all deal with carbon-based molecules, right? So, and it's really cool. They call aromatic rings. They form these ring structures, and these rings, they call them aromatic because they have smell associated with them. They make funny different smells, you know? So like, how many of you guys like licorice, black licorice? Anybody? Anybody
No.
like the way it smells? Or sambuca. Sambuca is an alcohol made from black licorice, the plant that makes black licorice, right? So anyway, so all of those things, strawberry, mint, all of those come from chemicals. And those chemicals are carbon-based chemicals, right? And so it's a whole field of study. It's really exciting, right? And you guys are going to get a sampling of it today. Right? So today we're going to be talking about organic chemistry. And then we're going to talk about some of the nomenclature associated with organic chemistry. And then we're going to move into the classic chemical nomenclature. So you guys can start seeing some of the differences. But I want to make sure that you guys have a base knowledge of that organic chemistry because it's going to be important later on. Okay? Are you with me? So what is the definition of organic? Cheyenne, organic means?
It has carbon in it, a compound that has carbon.
Good job. Okay. So now that we got that established, right? So I'm going to ask you a question. I want you to think really hard, really, really hard. And then Hector's going to give me the answer. Okay. So if something is said to be a hydrocarbon, okay, what do you think it has in it? If it's a hydrocarbon, what two elements?
Hydrogen and carbon.
Hydrogen and carbon. Good job. See, I knew he was going to give me the answer. So a hydrocarbon is something that only has hydrogen and carbon in it, like my plastic bag, right? My plastic bag is a hydrocarbon because it only has hydrogen and carbon in it, okay? So that's where we're going to start, is with hydrocarbons. Hydrocarbons can belong to a family. Well, they're a family. They're basically made up of only hydrogens and carbons. So we're going to start off with that. I'm going to write a couple chemicals on the board, and then you're going to tell me which ones are hydrocarbons. Okay. Which one of these molecules, or multiple, it can be more than one, are organic?
All of them are organic except for the last one.
Okay, so we'll put pluses by those that are organic. And then minus if it isn't. Which one of these are inorganic? Inorganic is basically everything else except things that have carbon in it.
The last one?
Okay, the last one. I'm going to add another definition. Those, some inorganic scientists will say if it has only one carbon in it, it's considered to be inorganic. as well.
And the second to the
CO3.
last one would
Okay. Okay, so which one of these are hydrocarbons?
Can I answer or should I let someone else answer?
Let's ask someone else.
Okay, cool.
Let's see, who haven't spoken up? Alexandria. Is she back? Brian, I haven't heard anything from Brian.
C6H14.
Okay. Any others?
That's it.
That's it. These are all minuses. Okay, piece of cake. Okay, good. So now let's talk about hydrocarbons, that you guys know what a hydrocarbon is, right? So the hydrocarbon can be broken up into three families. Here we have the first family is called alkanes. Alkanes are hydrocarbons that only have single bonds. Best way of saying it. Another way of saying it is that they're saturated with hydrogen, meaning that you have so many hydrogens that you only have single bonds, because again, carbon can form 4 bonds, right? So if it's saturated, all 4 bonds are going to be occupied by either a carbon or hydrogens. Okay, let me show you what I mean, right? So do you see any double bonds? Anyone see any double bonds there at all?
No.
No. Any triple bonds?
No.
No, right? So this is an example of saturated. So when we're talking about saturated fats, right, we're basically saying that these are long carbon chains that only have single bonds. There are no double bonds. Okay. We have the other family is called, or the like cousins, I guess, is called alkene. The alkene family has at least one double bond. So for instance, if we have this guy, okay? And then the next family is the alkyne. What do you think that means?
One triple bond?
At least one triple bond. Okay, piece of cake?
Yes.
Okay, good. Okay, so we have alkanes, alkenes, and alkynes. Alkanes, A, 1 bond. Alkenes, E, 2 bonds. Alkyne, Y, 3 bonds. Okay? Good. Okay, so that now that you've been introduced to that, you want to make it a little bit harder? You want to go with nomenclature? So let's see, I'm going to keep these guys up here because we're going to use these for naming later. But can I erase the definitions? You guys got that tattooed already on your arms and on your chest?
I do. I don't know about anyone else.
Okay, good, good. Okay,
I have my
so
appointment scheduled.
you have your appointment scheduled. Excellent. Okay, so we've been introduced to this guy before. So we'll start off with this guy. CH4. What is that guy called? Anybody? Anybody? It's open to anybody. Anybody at all. Let me give you a hint. Cow's fart.
Methane.
Okay. As soon as I say that, everybody knows what it is now, right? Methane. Now you notice methane ends with last 3 letters. Come on, you can say it out.
Ane.
Ane. Okay. So what do you think that first part is, right? Because it belongs to the alkane family. So what do you think that first part is going to tell me?
Can I answer?
No, you can't answer. You just answered one. Alan, I want Alan to answer for me.
Oh, okay. Sorry.
Let me give you a hint, Alan. I'm going to give you a hint. So we have, and I'll draw this one out too. Oops. So ethane looks like this. Okay, Alan, are you ready? Gonna help me out?
What's the question?
Okay, so we know that the ane lets us know that it's a single bond hydrocarbon, right? So what do you think this first part means? The meth and the eth. So this is ethane here, and this is methane. So this is ethane, methane, and this guy down here is ethane.
What does the meth mean?
Yeah, what do you think the meth means? And the eth for this one. And this guy is called propane. What is the difference between the meth and the eth?
The meth has 1 carbon.
And the eth has how many?
2.
And the prop has how many?
3.
Ah, okay. So good. We're getting somewhere, right? So you just told me that if it is a 1 carbon, it's a meth. If it's 2 carbons, it's eth. And if it's 3 carbons, it's prop. Okay, so if it's 4 carbons, it's bute. If it's 5 carbons, it's pent. If it's 6, what do you guys think 6 carbons is? Think about those Greeks.
Hex.
Hex. If it's 7, it's hept. If it's 8, it's oct. If it's 9, it's known. If it's 10, it's deck. If it's 11, it's undeck. If it's 12, it's dodeck. And we'll stop there because I don't want to be driving in all those chains. Okay, so now if it was all single bonds, we put that word A, N-E at the end of it. So it's propane in this case, because there's 3, 1, 2, 3, propane here, ethane, because it's 2. And then we call this guy methane. So this guy would be called 1, 2, 3. What do you think it's going to be called? Three carbons. Cheyenne.
It would be pro. I forgot how to say the E-N-E, but
Ene?
with the E-N-E at the end.
Ene. Propene. That is correct. Okay. And then this guy, Jason.
That one is ethine.
Right. Okay, piece of cake.
Kind of.
Okay, so now we're going to show you. How many of you guys like writing out all those C's and putting all of the hydrogens on them? Does that really turn you on? Does it get you all hot and bothered, sweaty? Right? Now, if it does, you probably have corona, right? And you need to go get checked because it ain't a lot of fun writing them all out, especially on Zoom. So since we are scientists, we try to find the easiest way to do anything, right? And since carbons could have really, really long chains, like could you imagine drawing out each of the C's for dodecane, right? No scientist likes to do that. So what we do shorthand, right? We make stick figures. So each point represents a carbon, and it represents the number of hydrogens that are needed so that it has 4 attachments. So in this case, this is how I would draw propane. 1, 2, 3. This would be my first carbon. This would be the second carbon. This would be the third carbon. This is the first carbon. This is the second carbon. This is the third carbon. And it's understood, that's a 3 really. Okay, it's understood that they have enough hydrogens so they reach their octet. Okay? We good so far? Okay, so I'm going to test your skills now. Now that we got this, right? And we understand this, we're like, you know, we're here, right? So let's go. I'm going to erase this guy down here. Okay, so let's say we have okay, what would be that guy's name? And how many carbons does it have?
It has 9 carbons.
Okay, so its name would be, so we'll draw those out to help us see them. That's 1, oops.
Wait, so also with that structure, is it also understood that it's single bonds as well?
Yep.
Okay, so yeah, then it'd be nonane.
No name. Okay, piece of cake? Or non-name? Okay,
Yes.
so when we're drawing the double bond, it looks like that. Although that looks like a flag, but it's not a, it's supposed to be a straight line. My straight lines aren't. Let me see if I can make it better. It's like this. Really, I have not been drinking, officer. Yeah, I just can't get them to go straight, so do that.
Do you
There.
only do the 2 lines on one side?
Yep. So this here would be your first carbon. This would be your second carbon. This is your third carbon, right? So what would this guy be called?
That's propene.
Okay. Okay, and then triple bonds would be like this. And triple bonds don't have that hook. One, two. So this would be 1, this would be 2, and this would be 3. So what would this guy be called? Brian.
For the bottom one,
For the bottom one.
propene or propine. How is it?
Propine. Yep. Okay. Piece of cake?
Yes.
Okay. So
Wait,
you're feeling
so
pretty-
I'm sorry. Can you give us, I guess, another example? I know that you can't see me right now. I just look like a creepy silhouette. Well, it lightened up now. But can you, for the alkynes, can you give us an example of the, triple bonds that are more than just 3
Sure.
carbon?
Yeah. Don't worry, we're working up to that, you know.
Okay.
I just wanted to test you out a little bit there. So, okay, so let's move forward, Ben. Feeling you guys got a good grasp on this so far, so we'll give you some more names. And then I'm going to add another layer of complexity because, this is too easy, right?
No, I think this is as far as you should go, especially for the exam too.
Come on, Jason, now. Okay, so let's see how my drawing was. Okay. And then let's do.
I have a question. What are those structures called?
They're called skeletal structures.
Oh, okay.
Carbon skeletal structures. Okay, there we go. So what would this guy be called? Let's see. Jennifer. No, Jennifer. Steve.
So it has 1, 2, 3, 6.
How many carbons
Hexene?
did you get?
6.
So that's 1, 2, 3, 4, 5, 6. And so we call that guy what?
Hexene?
Okay. What about this guy? Hector.
And time?
So you have 1, 2, 3, 4, 5, 6, 7. So did you say heptine?
Yeah, that's what I meant to say. My bad.
That's all right. Okay. So the key is we have to use the carbon's longest chain, right? So we have to make sure that we're counting. So this is where that that triple bond begins. That will be your second carbon. This is your first one. This is your second one. This is where that triple bond ends after the third carbon. That's the fourth, fifth, sixth, and seventh. Okay, so I'm going to ask you a question and I want you to think about this. Are these the same? But don't they have the same number of carbons? Six and six?
No, they're not the same.
What's different about them?
The double line is in a different place.
So you mean that I have to keep track of where that double line is at? Because, I did call this hexene, which it is hexene, but there has to be more to it than that, right? We got to let us know where that double bond is happening. So if you only have a single double bond or a single triple bond, it's real easy. The way that you distinguish between these two is you tell me where that double bond starts, right? And you always want to start, your numbering could either go backwards or forwards. So I could go 1, 2, 3, 4, 5, 6, or I can go, this could be my 1. Put this in red. Oh, not red, let's do green. This could be 1. Okay, that were really supposed to be green. 2, 3, 4, 5, 6. So you want to put the numbering so that it gives you the lowest number where that element is. So if we go 1, 2, 3, 4, the double bond would start at the 4, right? If we go 1, 2, 3, then the double bond would start at the 3. So we would name this guy it would be 2-hexene, right? Because that would give me the lowest number for where that double bond is located at. And then this guy would be called what do you think it's going to be called?
One hexene.
That's right. 1 hexene. Okay, you can see where the difference is between the 2 hexene and the 1 hexene, right? So the same thing happens with our triple bond. So what will we name this guy? Oops.
I don't think I really understand. Can you go over it again, if you don't mind?
Sure. So we have to use the counting of our carbons. There's 1, 2, 3, 4, 5, 6. So you want to set it up so that we have the lowest number on the functional group or the element that we're trying to identify. What is the functional group that we're trying to identify here? What are we saying that is different in this situation?
What do you mean?
What are we looking at? What is different about this than a single bond than this? What is the difference between this?
There's a double bond
It's a double bond. Where's the double bond located?
between the 2 and the 3.
Between the 2 and the 3. So we put the number, the lowest number that we can get, which is the 2 hexene. That tells me that my double bond is on the 2nd carbon. It starts on the 2nd carbon and it goes to the 3rd carbon.
Mm-hmm.
Do you get that?
Yeah, yes, sorry.
Okay. So what I'm asking you here is, can you tell me how to name this officially? Since there's only one triple bond. How would I name this guy? The one down there.
Would it just be one heptine or no?
Nope. Does it start on the 1st carbon?
Oh,
That's
it would be 2 heptine. Yeah.
That's right. So it'd be 2 heptine because that's where the double bond starts. But you're telling me where the double bond is located at. Okay. So what happens?
Yeah.
Oh, go ahead.
I think what was confusing me before was that you put the different numbers on that hexene one. So
Yeah.
I was like, yeah, I got kind of confused, but thank you for clearing that up.
Okay, so let's say we have two double bonds here. So the way that we handle 2 double bonds count again, always starting with the lowest one if you can get it. 1, 2, 3, 4, 5, 6. So it would be 1, 1, 3, hexadiene. Okay, so that means di means I have 2. If I had a third one, okay, that is a horrible line. I apologize. we do 1, 3, 5 hex triene. Because we're trying to get this. Piece of cake?
How do you know where to count from? Because I see in those two skeletal structures that you started counting from like opposite sides.
Yep. You want to find the lowest numbers possible. In this case, we have 1, 2, 3, 4, 5, 6, right? So let's go the other direction using the red. It works 1, 2, 3, 4, 5, 6. Both directions, it's the same numbers in this situation.
Mm-hmm.
Right? So if I had just that 2, right? Let's get rid of that guy. So 1, 2, 3, 4, 5, 6. My lowest numbers would be 1 and 3, where this would give me, if I went the other direction, 1, 2, 3. I guess it would be the same that way too, huh? No, it's 1. It'd be 1 and 3 here. This one will be 3 and 5, right? Yeah, 3. It'll start at 3 and 5, the red numbers. So that will give me a higher number. So then in this case, we always want to go with the lowest possible numbers. So I'd go with 1, 3 hex diene. Instead of going with, because my other option would be going with 3, 5. Those are bigger numbers, right? So you always want to have the smallest numbers on the most important functional group.
Okay, that makes
Okay.
sense.
Piece of cake so far?
Yeah, overall.
Okay, so I'm going to put a couple up there, and I want you to tell me how I'm going to name this. Okay. So I can erase all these right here. Yeah? No? Okay. The first one.
Octane.
Octane. Okay. The next one.
2-heptene.
Are you sure? Let's count the carbons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Dectene.
Okay. So 2-dectane. Dectene. Okay. And then the next one, or the last one. Oops. You guys don't know this. Let me erase a couple of things. I got carried away. There we go.
Is it 1, 7, I don't know how it'd be pronounced. Decline.
Oops. I misspelled that. Okay. Questions, concerns, Cash?
No.
Okay, are you guys ready for the next level of complexity?
Sure.
I guess we have no choice.
Oops. Okay, let's see. Oops, I didn't want to erase everything. Just don't erase this. Okay. So let's do. Okay, so our next level. Okay, so when you have a side chain, these guys are called side chains. So this guy is your main chain. So when you start having side chains, you want to try to find the longest main chain first and number it. 1, 2, 3, 4, 5, 6, 7, 8. And again, now you want to find the shortest distance to the one that's a priority. So now you have a side chain that is a priority, or that would be our longest chain there. But we'd start from this side because we want to try to get the shortest distance to that chain. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we'd write this as or methyl octane. Okay, so there's only a single carbon here on the that's attached to that fourth carbon. So that's the first carbon, second carbon, third carbon, and this is the fourth carbon. So it has only a single methyl group attached to it. So we take that one, since there's one carbon there, we call it methyl. We put Y, L, since it's a methyl group there. If it was an ethyl group, then we'd call this guy ethyl. If it was 2 carbons there. See. So ethyl would look like this. Where that's 1, that's 2. Okay, so then that would be for ethyl. If it was 3 carbons, we'd call it propyl. Okay. Questions, concerns?
No.
Are we ever gonna see the chains with double or triple bonds?
Yes, you will.
All right.
Yes. So, although for what you guys need right now, I don't think I'm going to go into it, but if there were doubles and triple bonds, let's say if this was a triple bond or a double bond here, right? So then you'd put, it would be ethyl enol. So the ethyl enol on it. I'm sorry, that would be an E, not a Y, sorry. Enol. If it was a triple bond, it would be a Y. Okay. But I promise not to do that to you on your first organic chem exam. Okay. So if we have, say we have this. Okay, again, you always want to find the longest chain. This guy, again, is still the longest chain. So in this case, this guy would be named it would be 4-ethyl di, oops, 2, 5 dimethyl octane. Okay. So is your brains fried yet?
Pretty much.
Yeah.
Okay. So the things that I want you to be familiar with. You need to be able to distinguish between a double bond, triple bond, and single bond, and identify which family they belong to. You need to be able to at least recognize the side chains, and there are side chains, right? And then if you can remember to count the carbons, the orientation. Okay.
I have a question. Why is it called dimethyl octane?
Because there's
Well-
two methyl side chains. There's
Okay.
one at the 2, and there's one at the 5.
Okay, so when you're writing out the answer, you're supposed to split it up into the ethyl and the methyl, and then
Then the
the
main
di.
chain,
Yeah, of course. And then the prefix indicates how many of those there
Yep.
are. Okay.
So you're telling me where they're located and how many you have.
Okay, gotcha.
Yep.
Thank you.
If you had another, you could have this happening, right? So then that would be trimethyl.
Makes sense.
And then we'd call that 5,5, right? 2,5,5 trimethyl.
Oh, okay.
You're telling me that I have 2 on the 5th carbon. Okay. Okay, so we'll pick this up and I'll start introducing you to more functional groups.